Hey y'all, it's Mr. G. It's the weekend, and I know y'all ain't trying to do all this, so let's make it fast. This image is here as a review, so if you like it, cool. Again, review, okay? So today is when we're starting to really push into talking about covalent bonds. So ionic bonds, again, you transfer an electron, they become oppositely charged, they are attracted, boom, okay? Covalent bonds form when nonmetals are sharing electrons or when they're rather fighting over them. Both elements want to gain electrons to fill their valence shell, so they have to share. No ions are ever formed, therefore they do not conduct electricity. And you see here in this image that the electrons are going to held in the center and they constantly fight over them. Now, so far we discussed single bonds, or when atoms are sharing two electrons only, but let's say we have two atoms that both need to share two sets of electrons. Well, maybe they can do it together. They can, okay? Oxygen's a great example of that. Oxygen, as we know, has an electron dot diagram like this. So it has two openings. Well, if I put two oxygens next to each other, boom, boom, they can bond twice, okay? So it is possible for one atom to bond twice to another atom. That is called a double bond. It is also possible for atoms to bond 3 times together. That is called a triple bond. In terms of the strength of those bonds, triple bonds obviously are going to have more pull between the atoms, so they're much stronger. That also means they have a lot more energy in them, so when they're broken, they release more energy. Single bonds are a lot weaker, easier to break, and so just only 2 electrons is not as strong as sharing 4 or 6, because every electron they share is equally attracted to both nuclei. Or are they? So now's the time for us to introduce another trend. This is one of the main trends, and it really falls into covalent compounds, and that is electronegativity. Electronegativity is the ability of an atom to attract electrons. This is directly coordinated with nuclear charge. The more positive the nucleus becomes, the more likely it's going to be to attract electrons. But it's also got something to do with valence electrons. So we need to be taking both into account. So the higher electronegativity, when a substance has a higher electronegativity, or an element rather, it means it's extremely attractive to electrons and will draw them in, gaining them. Or if it's trying to share electrons and it is really high electronegativity, it's going to hold the electrons a little closer to itself. Okay, so therefore, those elements that like to gain electrons, like nonmetals, are going to have very high electronegativity. Noble gases excluded. Noble gases have no electronegativity. Why? Because they already have 8 valence electrons. They have no need to attract anymore, so they have no electronegativity. That means that the most electronegative elements are going to be the halogens, group 17. Metals have very low electronegativities because they do not want to attract electrons. And we see on this chart here that it shows electronegativity increases, which is directly proportional to nuclear charge. It also shows that electronegativity decreases as you go down, which is also similar to nuclear charge due to shielding. Okay. The more shields we add, the less likely it's going to be for a nucleus to be able to draw in extra electrons. So, as I already mentioned, sometimes atoms just don't play fair. They don't. Covalent bonds are overall a great example of that, because they don't want to make one of them happy. They both want to be happy, so they fight over the electrons, but sometimes one of them's a little stronger. And so it is possible, you've probably seen it before, in a horribly unbalanced fight that one of them overpowers the other. And that's what you see in some covalent bonds. Some nonmetals are very greedy. There's 2 types of covalent bonds then. We have polar covalent bonds and nonpolar covalent bond. The term polar means basically that you have a positive and a negative end to the bond. Nonpolar means that they would both be essentially neutral. So nonpolar covalent bonds are when they're sharing equally, meaning both atoms are pulling with the exact same force. Neither of them is spending more time with the electrons. Neither of them has more visitation rights with the electrons. Polar covalent bonds have unequal share valence electrons. So one of them is winning out. It's pulling harder. It has more visitation of the electrons. They spend more time closer to its nucleus, and that has to do with its electronegativity. The higher its electronegativity is, the more likely it's going to be to draw them in. So to determine if a bond is polar is something that we'll do a little, but we don't spend a ton with it because it's more important if a molecule, to determine if a molecule overall has a net polarity than it is to determine if a bond itself really has polarity. But nonetheless, it is a standard and we will hit it. Polarity is determined essentially by taking the two electronegativities of the two atoms. So let's say we had a carbon-hydrogen bond. I would find the electronegativity of carbon, I would find the electronegativity of hydrogen, and I would just subtract them in order to make it positive, just figuring out the difference, so the larger number minus the small. We have some ranges here. If it's extremely small difference, that means it's nonpolar. Now that makes sense because if the difference is very small between them, neither of them is really winning in pulling the electrons, and so the electrons fall right in the center. If one of them has a significantly higher electronegativity, and therefore we have a bigger difference in electronegativity, we have polarity. Now, greater than 1.7 means it's ionic. Wait a minute. That seems weird. Why is ionic in here? Well, ionic bonds are really just extreme polar covalent bonds. So what they do is their electronegativity difference, is so high that one of them will pull so hard on the electrons that it pulls it all the way over. Boom, we've seen that. Sodium and chlorine. Sodium transfers an electron onto the chlorine because the chlorine, now we know, is extremely electronegative. It's attractive to that electron, so it steals the electron. So if they don't fully steal it, it's still covalent. But if they do fully steal it, that's when it's ionic. So now we're realizing all of these bond types are really all on one same spectrum. And that's a good thing to recognize, is that it's all just about attractiveness to electrons and where the electrons go. So now's a great time, if you don't already, please take out your Unit 5 Chemical Bonding, Covalent Bonds, and Polarity practice problems that I gave you guys to work on while you were doing your notes, because you may want to pause the video and answer a couple questions. We've already now answered questions 1, 2, and 3. We know the difference between polar and nonpolar. We've looked at how electronegativity determines bond type, and now we're getting into really the questions, starting with question 4, figuring out how to determine the difference between electronegativity. So in this case, we're looking at the bonds for MgCl2. Now, it doesn't matter if you're thinking about magnesium's bond with this chlorine, or if you're thinking about magnesium's bond with that chlorine, guess what? They're the same. Oh, of course I'm going to use blue on a blue background. They're the same. So I don't need to do anything regarding the fact that there's two chlorines, because when I'm looking at bond polarity, I'm just figuring out, is each of those bonds polar or not? Okay. In this case, I'm going to take magnesium, which is 1.2, found that right here on the table. FYI, this is on your formula sheet. Okay, I never expect you to memorize these. Now, I accidentally do sometimes, and you may as well, especially with something like fluorine being 4.0. It's like, whoa. But these are on your formula sheet, so you don't need to memorize them. Magnesium's 1.2, chlorine's 3.0. The difference between them is 1.8. According to our rules, that means that it falls into the category of ionic, which, by the way, those rules are also on your formula sheet. So all you need to remember really is how to determine bond polarity and what it means. You don't need to try to memorize any of these numbers, okay? Let's look at another one this time. So we have H2O. Again, we have done now a covalent dot diagram of water, so we know this is what it looks like, okay? But what we need to recognize here is that, yes, this is an OH bond, this is an OH bond, they're the same. So all we really need to do is determine the polarity of one bond, and we know if the other bond is polar. So hydrogen has an electronegativity of 2.1, oxygen has an electronegativity of 3.5. You do the subtraction, it is 1.4. That is extremely polar covalent, and in class we're going to talk about, actually on the next slide, and in class we're going to talk about what that ultimately means for the molecule itself. So since one of the atoms is pulling harder, what we need to realize is, okay, let's think about hydrogen and oxygen, okay? Oxygen is more electronegative. So yes, they are bonded like this, but if I'm actually thinking about where the electrons are spending their time, it is exponentially more on the oxygen end. So the electrons are going to spend their time more on the oxygen end because it's more electronegative. Therefore, when I have these little electrons that are being pulled towards oxygen, that makes that end of the bond become slightly negative because electrons are negative. The other end of the bond becomes slightly positive. This is how water has the ability to dissolve ionic compounds. I told you guys that it has a positive, the hydrogens are positive, the oxygen is negative. This is why. It's because oxygen is more electronegative, so it pulls the electrons in its direction, so they're going to be way down there on that end of the bond. That makes that end of the bond more negative than the other end, just because that's where they are. So we show that with what is referred to as a bond dipole. It's down here, okay? The positive end of the bond, basically it's an arrow pointing towards the more electronegative element, and then as a reminder, the positive end of the bond gets a slash across it to look like a positive sign. Let's look at some examples. Okay, so let's use a couple of the ones that we have already used up to this point, okay? So obviously, let's start with water. I'm trying my best with this because the pen is kind of strange, so if the electron dots look a little funky, then I'm sorry, okay? So what we see is when we look on our electronegativity table, hydrogen is 2.1, oxygen is 3.5. So oxygen is more electronegative. So what I'm going to do is in both of these bonds, draw an arrow pointed towards oxygen. Now, I'm going to slash the other end, so that reminds me that that end is the positive end, okay? We generally then draw a plus sign and a negative sign so that we can remember what that ultimately means, okay? Let's look at, oh, good, no, go back. Let's look at methane, CH. I think I accidentally zoomed in the whole screen. So, oh my goodness, now I went too far. Okay. You know, I could edit this out, but I just don't feel like it. So with this one, we look at the electronegativities, hydrogen being 2.1, carbon being 2.5. Now, admittedly, that's not a huge difference. It's only a difference of 0.4, which means this is technically a non-polar covalent bond, but there still is some polarity, right? The carbon is still going to pull the electrons in a little. So what we would still do is draw them towards carbon. Carbon being more electronegative, we draw our dipoles in towards carbon. Now, if you flip over, I am going to do one of your practice problems on your sheet right now, and that is PCl3. So phosphorus with its 2 unshared pairs, chlorine with its phosphorus has 1 unshared pair, meaning 2 electrons unshared. Chlorine has 3 unshared pairs, Cl boop 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 boop, Cl boop 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 boop. Okay. So what we have here, we need to look at their electronegativities again. Phosphorus has an electronegativity of 2.1. Chlorine is 3.0. So chlorine is more electronegative. The arrow points in the direction that the electrons are going to be pulled in the bond. Chlorine, being more electronegative, gets the arrow pointed towards it. Okay. That means this end up here at the top is going to become very positive, and each chlorine will become slightly negative. Going up to methane, I didn't do it on there, but that ultimately means that carbon is going to become negative, and each hydrogen will have a slight polar charge to it. Now, obviously, we're not talking about these charges being the same as an ionic compound. We're just referring to them being partially positive or partially negative. And so it's not going to be, as mentioned, all the way positive or all the way negative, but it is enough to make a difference. Yes, I changed the color because it was bugging me. All right, see you guys next class. Brain questions.